Hello, Jeremy.
Hello.
There's no one in the classroom here. We'll wait a minute or so. Oh, it's already a minute. Yeah. So, how are things?
Pretty good. Work's keeping me tired, but other than that, everything's going pretty well.
Yeah, it's hard to take classes when you're working. I cannot imagine. But you have to do, I guess, what you have to do. Yeah.
Yeah, I'd rather it this way than not at all.
Yeah. Yeah, you said you already delayed quite some time, right? And you got this chance.
Yep.
And why did you decide during this period of pandemic? Does it suit you, or is it that?
Well, I think I just kind of took advantage of the chance. I mean, I didn't know like whether I should wait any longer or not. I finally had the money and saved up and all that stuff, so I was just like, I might as well. And I thought about it, and it's like the online setup kind of made it easier, but I do look forward to going back to regular physical classes. And since I work at McDonald's, they're pretty flexible with that stuff anyway, so it won't really be a problem.
Yeah. I can imagine that. Yeah, that's what I hear from, I think, almost everyone in the class. There is convenience, but given a chance, you would like to be in the classroom, I suppose.
Yeah, it's much better.
Yeah. That's what I hear from everyone. Yeah. At least in physics. Yeah. Okay, Borden is here. I think Christian may not be here. I think he's supposed to be attending this APS talk, which was supposed to be his schedule was 1 hour behind, but they are uh, pretty much not able to manage. I guess they messed up with all the Zoom connections because there are about 10,000 people. I don't know how they manage it.
That'd be insane.
Yeah, with all these Zoom connections, I don't know. He said he was waiting for 1 hour and his thing has not yet come. Yeah. So he may not be there. Okay. So let's see. Oh, I haven't yet posted the homework because there were some diagrams needed and I changed my mind, and so I'll probably do it today, but I'll give it sufficient time for you guys to submit. I'm sure you will not complain about not having homework. Okay, so here we go. So homework 6. Is this readable or should I change the pen? The time
Pretty good.
Try that again?
It's still pretty good. It's a little light, but
Yeah, I think since it is online, let's be picky. Since you say it's light. Everyone is on the online. Oh, by the way, I wanted to ask, I always forget. I have not been using the mic. In this room, there is no problem, is it?
sounds fine in this room.
Yeah,
Okay. That's interesting, yeah, because some audio things are good here. Okay. So this is homework 6. I plan to make it due March 19th, but it will be a very less number of questions, just 2 problems also, reasonable problems. So, or else I will change to Monday. And we have midterm 2, March 26th. Next. Okay. Notice that we talked about dipole, magnetic dipole moment last time. Like in very simple terms, we have magnetic moment of a current carrying loop of wire is if you have a current I going through it, and there is an area A, and that is an N hat, where it is perpendicular to the area of the loop. So you have this loop of wire, that's your current I, and that will be your N hat. Notice the direction. If this was going in the opposite direction, if this was the case, then I would say this is my N hat. So how you get that is using your right hand rule. Have your fingers going in the direction of I, and the thumb gives you the direction of the magnetic moment. So that's what we have. And we also said if it is not straightforward, sometimes it can be a complicated current loop. It doesn't always have to be in the plane. And in that case, you have to use a slightly broader definition. That's R cross J. Remember, J is having velocity. So if I were to divide by mass, so there is an angular momentum structure in there. So often it is good to think of magnetic moment as charge. So the current has a charge in there, and then there is, if I were to multiply mass and multiply mass there, then this becomes an angular momentum. So this is angular momentum. So it's just that. But even if it's a complicated geometry, you can always split a complicated loop into simpler structures. And let's do an example in that context, just to clarify. So suppose, so this is an example. So let's say this is X, let's say Y, let's say this is your X maybe, sorry. So that's your X going slightly into the board. It's a perception there. And let's say this is Y. And remember, X, Y, Z always have to satisfy the right-hand rule. If X and Y is chosen, then Z, you don't have a choice. This has to be in this direction. You don't have a choice to make it the other way. Right? X crossed, so X hat crossed with Y hat has to be equal to Z hat. Right? That's the right-hand rule is implicit in this. And now let's have a current loop now. So let me say I have a current loop like this. That's current I. That's current I. It goes in here, and and let's say it goes vertically up. So the dotted lines doesn't have a wire in it. So it's like part of the loop is in the XZ plane and the other part of the loop is in the XY plane. What you do in that case is that you split this into two of them. So this is the total magnetic moment, and in general, you can split this into as many pieces as you want. And the general idea is that you can break any complicated loop into planar loops. So let me do this. So this is the same X and Y. So I have an XY loop there. So I keep that. And this time, really, I have this piece going in here. So that's part of the loop, but that involves me adding this direction of current in here, which seems like, oh, I have messed up, but then I have another loop, right? So there are two pieces in here. X, that's your Y, that's your Z, and this one will be notice here in one of them it is going in the positive X direction, the current is moving in the positive X direction, and the second one is going in the negative X direction. So effectively, we haven't added an extra current piece in here. So if I were to say this is the magnetic moment I'm interested in, so I simply vectorially add these two quantities. Remember the vector nature of the loops. So let's call this M1 plus M2. So M1 is the current magnetic moment from out of this loop, M2 from out of this loop. Each one does not belong there. Like we have added this extra piece, but when you put it together, the extra piece cancels out. Now it's very clear what's the direction of the current or the magnetic moment is. In this case, it is going the sense of direction. If I were to use my fingers, it is in the direction of Z. And so that's equal to Z hat times I times the area. Now I have to say that length in the X direction and the length in the Y direction. Length in the X direction times length in the Y direction. So let's let me put some numbers here. So this is Ly. So that could be Lx. And then there is an Lz. So in this particular situation, I only need 3 lengths. Like I'm saying, all these are parallel. In general, it doesn't have to be, but you can always break it up into smaller pieces. Plus M2 now is in the direction of Y hat. Correct? If I were to use my curl of the fingers, it's in the Y hat direction. And it's the same current I that is going through, but the area of this loop will be decided by the length in the Z's direction and the length in the X direction. So that's Lx into Lz. And assuming that we are given these numbers, you can actually put in the numbers and get it in. So that clarifies how you would add these magnetic moments together. So let's do one more scenario. Any questions at this stage? Okay, so since that was super addition, so oops, okay. So let's consider the scenario of a solenoid. Let's say, remember, a solenoid is a cylinder with a lot of loops in there, right? So that's, and I can keep going. So that's a solenoid. And the current I could be in this direction. And this is usually winded up, but each one is a circle, even though it is basically a helix with a pitch angle deciding how far it is. But if you were to really keep it closely winded, it's pretty much circular wise. And each circular loop contributes to a magnetic moment. And we know that, so there is a magnetic moment from this one. So let's say that's down here. The next one will be down here slightly below. The third one will be slightly below, and so on. So you will keep adding them all, right? So each one comes with a I times A. But if this is a continuous distribution, I can talk about so this gets switched over to adding vectors, right? If I have small gaps, that is actually adding a lot of magnetic moments together. But if it is really continuous, it is really, if I take this length to be small, then I can talk about a situation where this is simply a lot of dipoles being added up. Right? So this is lots of dipoles being added up. And here I would say a small element here has a length dm. It's like saying instead of talking about charge per unit density, we talk about dipole moment per unit length. So let me say dm per unit length is equal to a constant, lambda, let's say, that has a direction. And this is dipole moment per unit length. And it also has a direction. In fact, if you want to visualize this, and let's say this starts from one end and it goes all the way to infinity on the other end, but it starts from zero. Right? A solenoid which starts from the origin and goes along the z-axis all the way to infinity. This can be imagined to be, so there is a south pole, there is a north pole, right? That's a magnetic moment is nothing but a magnet, right? A bar magnet. So there is a south pole, north pole, so that's a moment. There is a south pole, north pole, south pole, north pole, and so on. Right? That's the same picturization there. And again, you can cancel these things. Notice that there is a south north, you can keep canceling them. And you might say that, oh, there is only one pole remaining. But so let's see what that is. So this is as far as the way we have constructed it, we have taken a lot of bar magnets and attached one behind the other. So in a sense, realizable in the lab also. This will be called a Dirac string. Dirac, because he was the one who analyzed this, and this is sort of interesting because this will connect with the idea of a magnetic monopole. So as of now, we are just saying that there is we have attached magnet one behind the other. Okay, so what is So let's try to calculate the field due to that. So remember, in magnetic dipole moment, let's say is M. We don't try to give it a structure. It is, of course, can be imagined to be a bar of magnet, or it can be imagined to be a solenoid, a part of a solenoid. But we don't have, it could be a point dipole moment, so there is an M there. And we have shown that vector potential due to a, oops, I have to move this. Right? The vector potential due to this magnetic moment is mu naught over 4 pi times M crossed with R divided by R cubed. And once I have the vector potential, I can get the magnetic field by taking the del cross, which we know how it will look like. It will look like the magnetic field due to a bar magnet. This will look like a bar magnet. And the expression is that of an electric dipole also. So that's a lot of similarity. But the vector potential is given by this. And now we are talking about lots of dipole moments along a line, along a string, if you want. So let's say this is our z equal to 0. So that's x equal to 0, y is equal to 0, and z equal to 0. So it's just 0, 0, 0. And along the line, that's your z-axis, and the dipole moments are somewhere here is a point, let's say 0, 0, z prime. So each point acts like a source of a vector potential. And let's ask, what is the vector potential at some arbitrary point R, which is x, y, z. And this is 0, 0 because now I'm on the z-axis. So that's the z-axis. So hopefully the picture is clear. So maybe I should, this is not a straight line. So this is the Dirac string, if you want. Let me draw that as, so that's a special source. Okay, so every point leads to M cross R. So a tiny element there. So let's say this is the tiny element we are talking about. That's a tiny element contributing to the A. So let's say that's dA. Contribution due to this tiny element is equal to mu naught over 4 pi times M. But now it is not M because this is dm, right? So this is a tiny, for a tiny, infinitely tiny, line element, the contribution to the dipole moment is also infinitely tiny, and let me say that's dm, which is going to be given by the dipole moment per unit length, lambda, right? Dipole moment density, if you dm crossed with how far you are from the dipole, but it is not r anymore. R is from the origin. If it was at the origin, this is a formula, but this is now not at the origin. This is slightly shifted on the axis. Let me call that r prime. So that's r prime. So this is r minus r prime divided by magnitude of r minus r prime cubed. So if the dipole was at the origin, it is this formula, but if I were to move it from the origin to some other place where this is an arbitrary point there, then it is r minus r prime. But this is on the axis, so that is a simplification. Any questions at this stage? Okay, so let's see what this is equal to. And if we want the total field at this point, we just integrate it, right? Integrate it on the whole axis of z. That's all we have to do. But first, let's write this in a simpler form. So this is equal to mu naught over 4 pi. If you want dA. dm, let's divide it, let's write dm by dz, right? So this is equal to dm by dz, and that is dz. In fact, the source is z prime, so we should put a z prime there. So we are going to sum over all the z prime, like everywhere on the axis. And crossed with r minus r prime, divided by r minus r prime cube. This is nothing but lambda, and let us assume that, let us consider the special scenario where dm by dz prime is equal to lambda times z hat. So all these magnetic moments are aligned on the z-axis, so we want to do the special case. So that's equal to, so as a z hat, I pull that out. No, I will actually keep it inside. So this is mu naught over 4 pi times dz prime times lambda, let's say, this is lambda, I pull it out, times z hat crossed with r minus r prime is x minus x prime, but x prime is on the z-axis, that's 0. I hat plus y minus 0 in the j hat direction plus z minus z prime in the z hat direction. So that's your observation point, and divided by 1 x minus x0 square plus y minus 0 square plus z minus z prime square, and the whole thing raised to 3 by 2. Same as what we do all the time, just that I have not yet introduced the integral. If I were to move to the next board, so that's the same as the contribution from a infinitely tiny element of at one point on the z-axis is equal to mu over 4 pi lambda dz prime times z hat crossed with, this is nothing but, notice that the z cross z is 0, so that doesn't contribute. So whatever is left out is just xi plus yj. And notice that's only dependent on the observation point, not on the source point. It's divided by, this is x squared plus y squared plus z minus z prime squared raised to 3 by 2. That's in the plane, xy is a plane, so let's use the cylindrical coordinate, xi plus yj, and then you have rho square is equal to x square plus y square. Also, if that is the case, z hat crossed with x plus xi plus yj is nothing but z hat crossed with rho hat. Sorry, rho, not rho hat. Z hat crossed with rho itself. But what is that equal to? So that's the same as z hat crossed with I. So what is that? X crossed with I. So that's minus x in the j direction, and z hat crossed with y. So out here minus y in the I direction. Is that correct? Okay, x crossed with I. X crossed with y is z. So z crossed with I is y. So this is plus actually, right? And z crossed with j is minus y times j. But that's nothing but, how do you say this? This is minus y sine theta, right? So this is sine theta, rho sine theta in the I hat direction plus rho cosine theta in the j hat direction. I switched, I wrote the I first. Oh, is that? Oh, I'm slightly off. Okay. But that's nothing but rho times phi hat. Because phi hat is equal to minus sine theta I plus cosine theta j. We have used this many times by now, you should be familiar, I suppose. So that's phi hat. So we have the simple expression that in the numerator, it is rho times phi hat, and this is all observation point dependent, no source point there, so the integral will not care for that. So what we have is contribution at the observation point is relatively simpler. So this is mu naught over 4 pi times lambda, and that is a rho, and that is a phi hat. All dependent on observation point, nothing depends on z prime. And the denominator is rho square plus z minus z prime square. Okay. Having seen that it does not depend on the source point, only on the observation, now I can do the integral. It's relatively simpler. So the total integral, which I'll call it the total field, has to be integrated from, it starts from the origin, z prime is equal to origin, to z prime is equal to infinity. If I do that integral, I should get the total vector potential due to this whole Dirac string, what we call the Dirac string. So that's A, the total vector potential at the point, observation point, is equal to, let's do this. So this is mu naught, let me say phi hat times mu naught over 4 pi, keep the lambda times rho, and this integral is from 0 to infinity z prime over rho square plus z minus, let me say z prime minus z the whole square, 3 by 2, it doesn't matter. Let me substitute. Again, these substitutions are also reasonably the same once again and again. So it's z prime minus z is equal to rho times tangent. Right, that's a suitable substitution in this integral. And dz prime is equal to rho remains fixed, so it's secant square theta d theta. And there is a rho also contributing from. So potential due to this Dirac string is mu naught over 4 pi times lambda rho times, this is when z prime is 0, theta is equal to, so z prime is equal to 0, so theta is tangent inverse of minus z over rho. Right. that's minus tangent inverse of z over rho. And when it is infinity, so if this is infinity, then that is pi by 2, right? Theta is equal to pi by 2. And dz prime is rho secant square theta, theta divided by, this is 1, there's a rho cube first of all, and there is 1 plus tangent square theta. Okay. Notice, first of all, so if I had kept, there was one possibility that this is an infinite solenoid, but the solenoid, very thin solenoid, right? We're not necessarily talking about a finite solenoid, but applicable in either way. And in that case, this will be minus pi by 2. So let's consider that simpler scenario of or let's keep this fully, and then we can always do that at a later stage. So that's equal to phi hat mu naught over 4 pi times, as a lambda rho square in the numerator, rho cube in the denominator, there's a lambda over rho. And whatever is left is minus tangent inverse of z over rho times pi by 2. And what is this equal to? This is secant square theta, that's secant cube. So overall secant square in the numerator, secant cube in the denominator. So there is one secant surviving in the denominator, which becomes a cosine theta. Oh, Christian, you're back. Did it work at all?
Yeah, they got me in about 1:40 right before the session closed. The breakout rooms finally, they kicked everybody out originally back to the lobby and then rebooted them. And then, but a lot of people didn't show back up. So there's maybe 3 people in the room, but there was more watching the live stream. And then they had a networking session for, it's still going on. I left it to come here, but I was in there for about half an hour, just kind of talking to some of the other presenters.
Okay, good. Okay, at least it worked. Yeah. Okay. Okay, that's here. So that's cosine theta, but that's integral is relatively easier, doable. So let's do that. So cosine theta integral is what? Sine theta, right? So that's phi hat mu naught over 4 pi. Again, remember this is a extreme limit of a south pole. Begin with south pole, north pole, south pole, north pole, and keep going. So magnetic moment starting from the origin. At the origin, you keep a south pole, and then north pole, south pole, north pole, and so on, because that's a magnetic moment you keep putting one top of the other. And its vector potential apparently is equal to, so this is sine theta, and I integrate this, that's sine theta, evaluated at pi by 2, and this is to be evaluated at minus tangent square inverse of tangent inverse of 0 rho. That's the same as phi hat. This can be simplified probably. Lambda over rho. Write sine theta in terms of tangent theta, so that whenever I bring this in, it actually takes a simpler form, right? So write divide by cosine theta and multiply by cosine theta. So that's the same as tangent theta times cosine theta, but write that as secant. Because secant is cosine in the numerator, cosine cancels, it gives you the time. And secant itself, write this as 1 plus tangent square theta. Why do I want to write it like that? The simple sine theta, you write it in this form so that whenever I put this limits, it has a simple structure. And that's a idea. So that's equal to phi hat mu naught over 4 pi over rho. And when it is pi by 2, of course, this dominates, the tangent theta square dominates, but then the square root is there, so it is a 1, which is easier seen in the top one, right? When it is pi by 2, sine of pi by 2 is 1. So that's just 1. And when I substitute the lower limit, there is tangent inverse. Wherever tangent theta comes, I will replace it with minus z over rho. So this is plus z over rho divided by 1 plus z square over rho square. Did I get the signs correct? I think so. Okay, so that's equal to phi hat times mu naught over 4 pi times lambda over rho 1 plus. I can cancel out the rho in the denominators on both. So this is z over z squared plus rho squared. Let's again see what that is equal to. Remember our geometry here. This is our origin. That's your origin. And everywhere on the z-axis, this is what we call the Dirac string, right? Start from the south pole, north pole, south pole, north pole, or magnetic moment, all aligned along the z-axis, and it goes all the way to infinity. And we have an observation point down here. So that's your z. So that's your r, that's your z, that's your rho. Right? And if you want in spherical coordinate, this will be your angle theta also. So z over, so this is z over r. So z over r will be actually what? Z over r is up here. So if I say that's my
The
angle.
tangent of 90 minus theta. Right?
Is
Oh
it
no,
tan?
not tangent. No, it's sine.
Sine.
Sine, right? Sine.
Yeah, sine of 90 minus theta, right? So that's the same as cosine theta. Right? Let's say it will be cosine theta because yeah. So what we have is the vector potential due to this very this is what we call the Dirac string is equal to, so this was called the Dirac string. Right? So the vector potential due to the Dirac string is equal to phi hat. So it's all phi hat means this is circular, right? And remember, this is vector potential. The magnetic field is different, right? And we will come back, and the magnetic field is very interesting for this. Lambda over rho times 1 plus cosine theta. That is all good, but we'll stop here. But what we are going to see is that, remember again, so just to give you a feel for what is going on. So again, I want to make this bigger. So this is your z-axis. So what we have done is that we have put a south pole, north pole, south pole, north pole, and south pole, north pole, and so on. So that's a magnetic moment. That's a magnetic moment. That's a magnetic moment. And we have kept doing that. And we have done it at a very continuous level. And we call this dipole moment per unit length lambda. Lambda is equal to dipole moment per unit length. And we said this is in the z in the z direction. So what is this equal to? Notice that I can either think of it this way, or I can think of this as a single piece, this as a single piece. Like I can combine the north and south. When you keep north, south together, it is, since you go all the way to infinity, there are two ways of looking at it. Either you can start from south and go all the way, or you can start from north and go all the way. If you do it this way, you can cancel away all these things, and what you're left out with is a single pole, right? And it seems like this might act like a monopole, and in fact, what we will show is that whatever A we found, if you were to calculate magnetic field, so this is what we will do next time. So we will calculate the magnetic field due to that. That's perfectly fine. We should be able to take a curl and get the magnetic field. That's perfectly okay. But what we will show is that, remarkably, the divergence of this magnetic field is actually not zero. The south pole actually survives there. So this is going to be not zero. This is going to be a delta function right at the origin. And of course, there will be this lambda showing up there. So the point is, this whole string, so we started again by arranging a bar magnet one on top of the other. We made it continuous. That was just an idealization so that we can do this calculation. But the point is that if you were to make a solenoid, like a coil, and take it all the way to infinity, it will act like the magnetic field due to that coil will have all the similarities to that of a magnetic monopole. So you won't be able to theoretically differentiate between this solenoid that is extending all the way to infinity and a magnetic monopole. Of course, you cannot take it all the way to infinity. That is a catch in there. And since you cannot, so in that sense, there is no magnetic pole. But if you're doing an experiment, you can at least idealize that. But with that tricky thing that you have to go all the way to infinity. It is like Christian evoked with fractals. Like the moment you truncate a fractal, it loses its property. So one has to be very careful when you do such an analysis. But nevertheless, we will take it, so theoretically, we can take it all the way to infinity, and we will calculate the magnetic field, and we'll take the divergence, and we'll show that, oh, this divergence is not really zero. It has a magnetic monopole structure in there. So that's an interesting part. And it's called a Dirac string. This structure is called a Dirac string. So look it up, interesting conclusions comes out of that. But I'll stop at this stage and come back and do that. Thank you.
Thank you.
Mm-hmm.
Yeah, so they did eventually get us back in.